Hello everyone, welcome to our presentation on the tool AutoGR, which is the first end-to-end geo-replication framework that can automatically transform non-replicated serializable applications into their fast geo-replication version with little user interventions and without compromising important system properties such as state convergence and invariant preservation. My name is Wang Jiawei. This is joint work with some awesome colleges from University of Science and Technology of China, University of Nevada, Reno, and Nanjing University when I was a master's student at USTC. To offer fast responses for users worldwide, many internet services replicate data across multiple geographically dispersed data centers. Geo-replication is a major solution to cope with ever-growing user base for internet services. However, geo-replicated services face an expensive wide-area communication problem, since concurrent user requests across sites must be coordinated for precluding incorrect behaviors. Strong consistency introduces high delay to user responses. Various fine-grained consistent models have been proposed for safety-avoiding coordination. State-of-the-art solutions can assist developers in identifying the necessary coordination, rely on programmers to drive sufficient application-specific invariants at high-level code specifications. Such a manual process is often very time-consuming and error-prone. Our work is based on the key observation that the side effects produced by the user request and application-specific invariants that programmers need to maintain are already implicitly reflected in the logic of the programs. Therefore, it is possible to automatically infer through a static program analysis of the code behaviors and invariant to detect potential conflict operations that need to be coordinated. For instance, to implement the withdrawal operation of a banking system, we must subtract from the current balance a delta which is specified by the users. This subtraction summarizes the intended code behaviors. To make this subtract happen, we must check the code to make sure amount to be withdrawn should be less than or equal to the current balance. This checking reflects the intended invariant that the balance must always be non-negative. Following this insight, we propose AutoGR. The goal of it is to develop an end-to-end framework to automatically deploy non-replicated serializable code in a geo-replicated setting to explore performance benefits while maintaining the correct application semantics. Driven by a novel static analyzer Rigi, AutoGR can extract application invariants by verifying whether their geo-replicated versions obey the serialized semantics of the non-replicated application. AutoGR integrates Rigi with an existing geo-replication and coordination system Olisipo. The runtime of AutoGR automatically deploys the geo-replicated application, so carefully coordinating the operations confined by the restrictions generated by Rigi between sites. Rigi is comprised of a data specification library, a side effect collector, and a rule checker. DBLab represents the abstraction of relational databases in D3PY, a D3 API in Python. It covers a substantial range of SQL features and serves as a building block for Rigi. Collector inspects the source code and identifies side effects generated in different code passes. It gathers the path conditions leading to particular side effects. It also translates the side effects and their path conditions into code in D3PY. Checker calls the D3 theorem prover and generates restrictions through commutativity and semantics checks or pairs of operation side effects and their path conditions. The database abstraction in D3 covers the table schema definition and a substantial range of SQL features, from simple queries such as select and update to the advanced SQL features, ranging from comparison operator to aggregation. The left two figures show the translation of a table definition in SQL into an extension array in D3PY, which consists of pairs of key value, where key represents the unique index of the corresponding table that may include one or more attributes, and value covers the remaining attributes. The right two figures give the translation of an update query, which is translated into select and store operations on D3PY arrays parameterized by the primary key. The mission of the collector is to collect side effects and their corresponding path conditions and translate them into D3PY code. It first builds an abstract syntax tree from the source code of the target application to obtain the control flow graph. Then it traverses the entire control flow graph to identify passes with a deep-first search algorithm. We skip passes that are either read-only or leading to abort, since they do not generate side effects. Then we iterate our remaining code passes and collect the side effect for paths by performing one-to-one direct translation from Java code to D3PY code with the following two exceptions. First, we ignore control flow condition checks along the target path, which will be handled by the condition collecting phase. Second, for every encounter SQL statement, we translate it into its corresponding form using our extended DB-lab APIs. In addition to side effects, Rigi gathers the path condition by making conjunction of Boolean formulas of every branch taken by the corresponding path. We also extended the collector to incorporate the following two advanced features for partial considerations. The first one is conflict-free replicate data types. For example, we can use a simple last right ring strategy as an example, which resolves conflicting updates by determining an abstraction order over those updates and pick up the last right to be the final value. The second one is uniqueness, which supports the database's auto-incremental feature, ensures that a unique number is generated automatically whenever a new record is inserted into the table. To ensure our proposal is correct, which means that for any application, the geo-replication version of it does not generate unexpected behaviors compared to the non-replicated serializable version. We need to perform two checks, namely the commutativity check and the semantic check, to figure out the conflicting side effect pairs. The first one checks the commutativity of side effects to ensure the convergence of the system. Here in the figure, two concurrent requests of the update customer operation are submitted to two data centers to change the location of Bob from New York to London and France, respectively. When the side effects of the two requests were replicated across the two sites in different orders, the resulting states will differ. To preclude this kind of anomalies, we need to check the commutativity of side effects produced by operations in a pairwise fashion and add a restriction to coordinate the generation of any pairs of side effects that do not commute. The second check checks for any two operations A and B. If the side effect of operation A can be generated without seeing the side effect of operation B, then it must be able to be generated when seeing the side effects of operation B. For example, in the figure, imagine we run two withdrawals simultaneously against an initial state where they want to withdraw 50 and 60 from the shared account respectively. If the first withdrawal sees the side effect of the other one, then the side effect of it will never be generated. Thus, Rigi automatically adds a restriction over the two operations. To demonstrate the power of AutoGR, we access four web applications: small bank, Rubies, six reservation, and health pass. The first three benchmarks has been widely used in related work, and the last one is a real-world deployable application. The simplest application, small bank, simulates an online banking system. Rubies emulates an eBay-like online auction website. This reservation models an electronic airline ticketing service. Health Plus is a management system for healthcare facility. Here we show the main static analysis result of Rigi. First, it reads the database organization files to produce the district-wide specifications about the table data structures. For this purpose, Rigi generates 29 to 542 lines of database specifications for the four applications. Second, Rigi traverses all code paths and created 119 to 1,387 and 38 to 1,113 lines of side effect and path condition specifications, respectively. We then evaluate Rigi and the normal mode, and the optimal mode, which enables the two commutative transforming features introduced before. When switching from normal to optimal, the restriction rate for small bank remain unchanged, but the restrictions of Rubies and health paths are greatly reduced. Rigi takes from 24 seconds to 1.5 hours to analyze all four applications. Additionally, with 16 threads, Rigi introduced 3 times to 12 times speedup of the static analyze time for the four applications. For example, for the largest improvement, it reduced the time cost of analyzing health paths from 1.5 hours to 7.7 minutes. Thus, we conclude that given the analysis is a one-time and offline job, the cost is moderate, and Rigi scales well to applications with larger size. We run geo-replicated experiments on Amazon EC2 virtual machines across 3 data centers to see the runtime performance of AutoGR. As shown in those figures, compared with state-of-the-art human intervention-free automatic approaches, AutoGR reduced up to 61.8% latency and achieves up to 2.12 times higher peak throughput compared with state-of-the-art approaches relying on manual analysis. AutoGR can quickly enable the geo-replication feature with zero human intervention while offering similarly low latency and high throughput. Thanks for your listening.